Particle Physics 2019 Higher Level Question 12a Part 1. So it's not often we see particle physics coming up in question 12, it's normally question 10, but in some years it's come up as part of question 12 and question 11. So in this question here we have the Swiss franc, which has a picture of the Large Hadron Collider on it, so they're kind of using that as a bit of an introduction to the topic. But the first question that they ask us starts here, where we're looking at the two families of hadrons. So let's number the parts in the questions. So the first one is to name our two families. The second one is looking at explaining why we have a neutral particle produced. The next part of the question is looking at a calculation. And the next part is looking at how protons are maintained in circular motion. And the next part is looking at advantages. Okay, so we have 5 parts to this question. So if we look at the first part of the question, it says there are two families of hadrons. Name the two families and distinguish between them. So with the hadrons, we basically have the baryons, and the baryons are basically made up of 3 quarks. Okay, and the second family of hadrons are the mesons, and the mesons are made up of 1 quark and 1 antiquark. And it doesn't have to be the antiquark of the quark, so you could have an up and an anti-down, okay? So the next part of our question looks at this collision, right? So we have 2 protons and each have a velocity of 0.9 c, which means they are 0.9 times the speed of light, and they're travelling in opposite directions and they collide. And we're told that we have a neutral pion and 2 protons remaining after the collision. And it says the single pion produced must be neutral, right? So this pi to the power of 0, the 0 is telling us that's neutral. And they're saying, well, why is this the case? Well, let's look at that collision. So we have a proton and a proton. And after we have a proton and a neutral pion. So it has to be neutral, because if we look at our charge, well, beforehand we have a proton which is +1 and a proton which is +1, so we have a charge of 2+, and after we have a proton and a proton which is 2+. So therefore, in order for it to be balanced, there has to be neutral charge here, right? It has to be neutral, because otherwise this wouldn't be balanced. And our answer to the question would be then, therefore, must be neutral because of conservation of charge. Okay, so we were getting 3 for stating our baryons and our mesons as the two families, and 3 for distinguishing between them. And then we were given 3 for mentioning conservation of charge. So that was the key to the answer here, that we have to conserve our charge. So the next part of the question then is our calculation. And it says calculate the total kinetic energy of the 3 particles after the collision. So they're referring to the 3 particles, in other words, the 2 protons and the pion. So we're looking at the total kinetic energy. So basically beforehand you have 2 protons tearing towards each other with a speed of 0.9 times the speed of light. And once they collide, all of their kinetic energy is then going to be used up to make the pion. Okay, so in other words, we have energy before must equal energy after. and we're going to have all of the energy being used up to make the pion, and any leftover energy would be the kinetic energy of the three particles. So let's look at this question. One thing to note is the only piece of information given to us about anything here is the velocity. There's no other numbers involved in this question, which means we have to refer to our maths tables. Okay, so let's set up the question. So we have our proton beforehand, our proton, and our neutral pion afterwards. So for setting up the question, the first thing we want to look at is what pages in our tables are we going to be using? Well, we're going to be going to page 46, 47 and 48. Okay, so I'm going to state my energy before must equal my energy after. And therefore, if I'm looking at beforehand, we have our kinetic energy is a half mv squared. So we have two protons, okay? So I basically need mass and velocity. Well, I know the mass of my proton from my maths tables, which is page 47, okay? And if I go to page 47 there in my maths tables, I can see my mass of my proton is 1.62171 by 10 to the power of minus 27 kilograms, okay? And I'm told the velocity is going to be 0.9 times the speed of light. Now the speed of light is given there again on page 47 in our maths tables, and that's 2.99792458 by 10 to the power of 8. Okay, and then that will be in meters per second. So if I'm looking at the kinetic energy beforehand, I have two protons. So therefore, it's going to be the same kinetic energy for each colliding proton. So therefore, it's going to be 2 times a half times the mass, 1.6726271 by 10 to the power of minus 27. And then times the velocity, 0.9 times the speed of light. And it has to be the speed of light, 9792458 by 10 to the power of 8. Okay, and of course it's v squared. So if I put that into my calculators, well, what do we get? So we get 1.217654713 by 10 to the minus 10, and that's joules. Okay, so that is the kinetic energy of the two protons colliding. Okay, so after then, what we have is a pion is created. So basically we need to know as well what energy is going to be used in doing this. So what is this energy conservation? So we know that energy from Einstein's equation is the change in mass times the speed squared. So if I'm looking at the mass defect here, well, we have the mass before minus the mass after. Okay, well, what's our mass beforehand? Well, it's basically 2 protons. And what's the mass after? Well, it's 2 protons and it's going to be a neutral pion. So in other words, the mass defect is going to cancel out our 2 protons, and basically we have our change in mass is going to be the pion. Okay, now if we go to our maths tables on page 48, so we had the speed was page 47, okay, and then for the pion we have to go to page 48. Now what's interesting here about the pion is that it doesn't give us the pion's mass. Instead, what it gives us is the relative mass, okay? So for the pion, we're told the relative mass is 264. Now what that means is that if you look at the top of that table, it's 264 times the electron, the mass of the electron, okay? So basically what we have here then is 264. So and again, obviously that's giving us negative here, but it's the absolute value we'd be looking at. So we have 264 times 9.10938 0938 by 10 to the power of minus 31. And that gives us a mass defect of 2.4048762 by 10 to the power of minus 28. And of course that's kilograms. Okay, so therefore if I look at the energy, well, the energy is going to be the mass, change in mass, and that's times the speed of light squared, and of course that's 2.997924 92458 by 10 to the power of 8. And we always have to be careful when we've got so many digits going on in these modern physics and particle physics questions, but of course every digit counts, otherwise you end up with a huge discrepancy, okay, because they're such tiny numbers. So if we put that into our calculator, what does that give us? Well, it gives us 2.16139547 by 10 to the minus 11, and that is in joules. So what is this energy? Well, basically this is the energy needed to make the pion. So this is energy is used to make the pion, the neutral pion. Okay, so that energy is being converted into the mass of the pion. So therefore, if the energy is being used up to be converted into the pion, well, is it the same as the energy we had beforehand? Well, clearly it's not, because we have 1.217654713 by 10 to the power of minus 10 joules, which is more energy beforehand than this energy needed to make the pion. So that means there's leftover energy. So therefore that leftover energy must be the kinetic energy of the particles. Okay, so we say therefore the leftover energy is used as kinetic energy for the 3 particles. So it's a bit like in the photoelectric effect, you have the threshold frequency, which gives you your work function. So that energy just needed to break free the electron. And then if there's any extra leftover energy, it's used as kinetic energy. So as the frequency increases, you get more leftover energy. So it's the same here. We have the energy required to make that particle, and any leftover energy is then used by those particles as kinetic energy. So our leftover energy then is going to be the kinetic energy of the 3 particles. So the 2 protons and the neutral pion is equal to, well, what did we say there? We had 1.2176547 13 by 10 to the power of minus 10, and that is minus our 2.161395047 0.47 by 10 to the power of minus 11. And then what does that give? So we're left with then 1.001515208, and that's by 10 to the power of minus 10, and that is joules. So really nice, good, juicy calculation, that good bit of thinking involved and good use and understanding of your maths tables. So really important there, as you can see, this one especially, you need to be highlighting, like how would we get the mass? So it's the relative mass. So it's the relative mass times the mass of the electron. And then of course the mass of the proton and the speed of light. You know, the speed of light wasn't given to us, so I wouldn't take it to be 3 by 10 to the power of 8. If they're not giving you values in your maths table, or if they're not giving you values as part of the question in the leave insert, always take what is in your maths tables, literally every single number. Okay, so what were the marks then for the calculation? So we had 3 for our half mv squared, so for the actual formula. We had 3 for getting the energy beforehand. We had 3 for getting the energy after, so for setting up our energy after. And then 3 for getting your answer. Okay, so we had 12 marks in total for your calculation. Okay, so the next part of the question then is part 4, how are protons maintained in a circular motion? So if we're looking at how protons are maintained in a circular motion, well, it is the magnetic fields. We saw in CERN, obviously they use huge superconducting magnets using helium to cool them down, and it's these magnetic fields then that allow them to provide the centripetal force to keep them moving in a circular motion. In other words, around the circular particle accelerator. And there was 3 marks for that. Okay. Now, if you're looking at marking schemes and they have things in brackets, that year they actually had provide centripetal force in brackets. That means that they would love you to have that in your answer, but some students don't do it, and therefore they kind of make changes to the marking scheme. But originally the marking scheme would have said you had to say magnetic fields to provide the centripetal force. You know, that's really the definitive answer. Okay, so then the last part of the question was part 5, and it says state the principal advantage of the circular accelerator over the linear accelerator. So why is the accelerator in CERN much better than what Cockcroft and Walton were using back in the day in 1932? Well, basically what we can have is we can have greater energies reached. Well, why can we have greater energy? Well, of course, because you can continually speed them around, so therefore they're going to reach higher velocities, and therefore if they're reaching higher velocities because they're going around and around and around, then you're going to get greater energy. Okay, you also have a longer path, and because it's a longer path, what that basically means is that it can go around continuously in one circle. So it's a longer path, whereas if you have a linear particle accelerator, you're limited to how long it can be because of how much space it's going to take up. So of course that means then that the circular particle accelerators are also more compact. In other words, you get more whack for your money in one space. And of course then what we can have obviously is we have that continual circular path rather than just trying to spread it out over a huge, long distance. And there was 4 marks going for that question. So we just had to give one answer to get that. So it says state the principal advantage. So it doesn't say state advantages. Okay. So nice question. So what I'm going to get you to do now is what you're going to do for me is you're going to do 2008 question 10 and 2011 question 10.